Hey everyone, let's jump right into this explainer. Today, we're totally unpacking the mechanics of engineering statics, looking specifically at rigid bodies and equivalent systems of forces. You know, if you've ever found yourself looking at a massive bridge and wondering how engineers know for sure it won't collapse, or how a towering crane doesn't just tip over, well, you're in the right place. We're about to make those invisible forces completely visible. To really ground this in reality, just picture a massive cargo ship. Have you ever wondered how those tiny, kind of insignificant-looking tugboats can possibly predict and control a vessel that literally outweighs them by thousands of tons? Well, they aren't just guessing. The secret sauce here is the rigorous mathematics of statics. By totally understanding the specific points where they apply force and the exact angles of their push and pull, they create a perfectly controlled system. So here is our roadmap for today. 1. Intro to rigid bodies. 2. Internal versus external forces. 3. Moving forces, transmissibility. 4. Moments, tendency to rotate. 5. The vector cross product. And finally, 6. Varignon's theorem.
Let's kick things off with sections 1 and 2. Rigid bodies and forces, focusing on internal versus external.
You know, in the real world, we can't always just pretend an object is a tiny single dot. Its actual size and shape completely dictate where a force hits. Think about people physically pulling a heavy truck. When engineers draw what's called a free body diagram of that exact scenario, they completely ignore the internal forces, like the friction between each individual wheel and the axle it's mounted on. Why? Because those internal forces don't actually move the truck as a whole. Instead, we only care about the external forces, the weight pulling down from the center of gravity, the upward push of the road on the tires, and the forward pulling tension of the rope.
And we literally see these external forces constantly at play in simple everyday machines too. Whether you're using a pair of scissors, pushing some dirt in a wheelbarrow, or just prying a stubbornly stuck lid off a paint tin, you're always relying on 3 key components. You've got a load, a point of effort, and a pivot, or fulcrum. Truly understanding where these external forces interact with a rigid body, that's the absolute foundation of all mechanical engineering.
Moving right along to section 3, moving forces, also known as transmissibility.
Okay, so now that we've identified our forces, here's a really cool trick for how we can slide them around to make our math way easier. It's called the principle of transmissibility. It states that you can slide a force anywhere along its invisible line of action without changing how the object moves or rests. So, you can take a force pushing on the front of an object and literally move it to the back, as long as it stays on that exact same invisible line. The physical conditions stay perfectly identical. They're what we call equivalent forces.
To put that into a practical, real-world perspective, pulling a truck from its front bumper with a specific amount of force has the exact same mechanical effect on its forward motion as pushing it from the rear bumper with that identical force along the same horizontal line. The truck doesn't know the difference. Mathematically, it is exactly the same thing.
Which brings us to section 4, moments, and the tendency to rotate. Up until now, we've just been talking about pushes and pulls and straight lines. But what happens when forces don't push straight and actually cause an object to spin or bend? That's where we get a moment. A moment is simply a measure of the tendency of a force to cause rotation around a specific point. If you've ever used a wrench to tighten a bolt, you have applied a moment. And the formula is beautifully simple. The magnitude of the moment just equals the force, multiplied by the perpendicular distance from the pivot point. Basically, if you want more turning power, you either push harder or you get a longer wrench.
What's super interesting here is how we can visualize this invisible spin as a 3D vector. You can physically find the direction of this rotational force using what's called the right-hand rule. Seriously, hold up your right hand right now. Curl your fingers in the direction of the rotation, sweeping from the radius to the force, and stick your thumb straight up. Your thumb is pointing perfectly along the axis of the moment vector. This vector is entirely perpendicular to the flat plane where the pushing is actually happening.
And engineers have a very strict convention for this. If a force causes a counterclockwise rotation, that gives us a positive moment. Your right thumb points straight out toward you. But if a force causes a clockwise rotation, that's a negative moment, and your thumb points away from you, diving right into the surface.
All right, section 5, the vector cross product.
So we've seen how rotation behaves physically. But to accurately calculate these invisible vectors, we have to step into the world of 3D math. Finding a moment in 3 dimensions requires a mathematical tool known as a cross product. When you take the cross product of 2 vectors sitting flat on a plane, it always generates a brand new vector. And this new vector stands completely perpendicular to that original plane. It perfectly, mathematically maps exactly what we just did with our right hand.
But wait, here is where you have to be super careful. This isn't your standard elementary school multiplication. Regular math is commutative, right? 2 times 3 is exactly the same as 3 times 2. But vector cross products are strictly not commutative. The order absolutely matters. Swapping the vectors literally reverses the direction of the force. So multiplying vector p by vector q gives you a totally different result than q times p. In fact, it gives you the exact negative.
You can see how this non-commutative quirk plays out on a standard 3D grid. Think about our unit vectors: I for the x-axis, j for the y-axis, and k for the z-axis. If you multiply the j-axis by the i-axis, you get a negative k vector pointing straight down. But flip that around, I times j, and you get a positive k vector pointing upward. The rotation flips, so the resulting vector flips. Order is absolutely everything in statics.
Finally, let's wrap up with Section 6, Varignon's theorem.
To cap off all this complex math, I want to show you the ultimate engineering shortcut for dealing with multiple, chaotic forces acting on an object all at once. I know the theorem itself sounds incredibly dense on paper, but Varignon's theorem is brilliant. It essentially proves that you don't have to calculate one massive, confusing rotational force from some weird, complex angle. Instead, you can just easily break the force down into its simple horizontal and vertical components, calculate their individual smaller moments, and then just add them up. The sum of the parts perfectly equals the whole. It literally saves engineers countless hours.
So, as we wrap up this explainer, I've got a challenge for you. Try to change how you look at the world. Just look at the objects around your room right now. From the heavy hinges supporting your door, to the structural beams over your head, right down to the joints in your very own body acting as pivots. Can you see the invisible statics acting upon them? The vectors, the moments, the delicate equilibrium keeping it all from collapsing? This math is literally everywhere, holding our physical world together. Thanks for learning with me today, and definitely keep exploring.